Today we're going to be doing a training for the settlement of an embankment, and we're going to compare this by two different methods in the program GTSNX, one of them being fully coupled and the other being the consolidation. So we will be importing the geometry and then also importing the materials and jump right into meshing and assigning various kinds of boundary conditions that are relevant for one or the other methods, as well as the definition of the water levels and the stages themselves, and then we'll be comparing the results. But this is a basic layout of what our 2D model will look like. So we will be, through one method, seeing the settlement of this embankment by the weight itself, and by another we will be creating a boundary condition for suction and actually comparing the two results. So we'll be looking at things like initial and long-term settlement, compressibility, and other things such as drainage for improvement of the soil. And we'll be having, the soils will be two sand layers, one above and one below, and then the middle layer will be clay. I'll be using a consistent modeled chem clay for that. So here are the materials themselves. As I mentioned, these will already be inputted into the model that we're going to be practicing. And then, as I also pointed out, most of the materials will be just elastic, but the main one will be focusing on the middle layer, which is where we'll see the draining and the settlement, the compaction will be using modified chem clay. So this will be a 2D model. So we'll actually have 3 analysis cases. As shown, we will be doing one analysis case by the fully coupled method, where the settlement is actually created by suction drains. So we'll have the initial state ground, and then in a later stage apply a suction, and then have a leave time. And we'll be looking at the settlement due to the pore water pressure being sucked. And then we'll actually be comparing these results to 2 other cases in which we'll be activating an embankment instead of creating a suction condition. So in these 2 cases, there'll be more one-to-one related. One will be fully coupled method, and the other will be by that consolidation method. So we're actually going to take a little closer look at the differences between these 2 methods. But basically, the construction stages will be almost identical. The only differences between these 2 will be the boundary conditions. And then, so as I mentioned, in the end, we'll look at all 3 cases results, key results. So just a quick recap. Recently, maybe last month, if you attended to one of our trainings, we did analysis for what would be semi-coupled, which is the seepage stress change, sequential change. So you can think of the semi-coupled analysis as a sequential analysis. So basically, you have one stage where you consider the seepage analysis, you create results for pore pressure, and then those results of pore pressure are passed on to the next stage, which is a stress analysis, so that they can consider the pore water pressure in those cases. But this is a one-way communication. Whatever changes you have in the stress stage, for instance, an excavation or some sort of compression, if that affects the pore water pressure, that is not reflected back. And so it's almost like stepping stones or steps, sequential steps. However, in the fully coupled analysis, it's actually both are considered in a single stage at the same time. So any changes in compression of the soil that forces water out will be reflected, and vice versa. If there's like an additional or a suction created, some other boundary condition related to seepage, it will be directly reflected in the stress. And this is actually done over the same, it's a time-dependent analysis. So that is the main difference between what would be these 2 kinds of analyses. And the other one that will be the main focus today will actually be the fully coupled versus consolidation. So they actually have some similarities and then some key differences. The similarities is that for both cases, you can consider the stress and the seepage conditions in the same stage, and they're both time dependent. However, the main differences are in some of the initial assumptions and some of the boundary conditions you can use. So for instance, consolidation analysis assumes that there's a steady state water pressure, so that you define your water level and it's going to be the same. And it also, by defining the water level, you just define a water table. So it assumes like a uniform distribution of the hydrostatic pressure. And the results focus more on displacement caused by excess pore pressure change, dissipation. Whereas for the fully coupled analysis, you can simulate any kind of hydrostatic initial condition. There's no assumption of steady state. So you can use seepage boundary conditions such as flux or total head or pressure head and create your own distribution. It doesn't have to be uniform throughout the layers. And so this gives you a more realistic scenario, especially for the initial conditions, of what would be happening related to the pore pressure for your project via an excavation for a tunnel or a settlement of an embankment or whatever. So in certain cities or certain parts of the world, this is where this becomes critical. For example, in Mexico City, they built the city above a lake bed, and there are higher concentrations of pore pressure at different depths of layers. So that cannot be captured fully by just defining a constant hydrostatic pressure. You have to use these kind of advanced seepage boundary conditions, manually defining pressures at different layers to capture that. But the idea being that the program does allow you to do that, and the fully coupled analysis is how you go about it. So these are the main boundary conditions that we'll be using today, and I'll quickly just review how these are used by some methods and not by the others, and vice versa. So the most basic way to define the water level would be just to use this command, where you can select via a line or a surface in case you're working in 3D, and it'll create this water level automatically, and will just give an even distribution, increase of hydrostatic pressure on the way down. So this is how you would define your water level for a basic stress analysis or for your consolidation analysis, so it's steady state. Whereas for fully coupled, which would be similar to the seepage that we've seen in other trainings, you can use all different kinds of boundary conditions like nodal head or nodal flux, where you can manually select nodes and either directly define the head or the pressure. And you can apply multiple sets of these boundary conditions for different layers. So this is how you can control if there's like a concentrated hydrostatic pressure or concentrated conditions such as a drainage condition. You can apply these advanced boundary conditions for that. Consolidation analysis, or actually these can also be used for fully coupled, but they have additional boundary conditions. One of them being the drainage condition, where you select the nodes or you select lines, layers, and it's telling the program in the calculation that the excess pore pressure should go to 0 at these boundaries. And the other being the non-consolidation boundary condition. So all the elements have your normal displacement degrees of freedom and your rotational degrees of freedom, but there's an additional 7th degree of freedom that's related to the pore pressure. So if you activate this boundary condition on the elements, that is basically turned off, and so it would be reflected as only 0 for pore pressure for those layers, or not even considered at all. So these are specific boundary conditions that can be used as well. But what we'll be seeing actually is that for the fully coupled, you can create these drainage conditions using seepage boundary conditions, where you can actually control and hence even create suction, like negative pore pressures, instead of only relying on a drainage condition that's general and setting it to 0. So consolidation in itself is a little more basic, if you will, or has a lot of assumptions that the fully coupled allows you to control or account for. So this would just be a quick summary. Again, comparing between the semi-coupled and the fully coupled. Actually, in the end, we'll take a look at a 2D case that we've done in the past, a semi-couple of an excavation with changing water levels and comparing those results to the fully coupled. But what we're showing here is that if you're doing semi-coupled, you cannot see the change in what would be even a drainage condition. So you either have to start a stage where the water is full or where the water is completely drained, and then switch in between. But then fully coupled, you can actually see that change over time, that stress-strain relationship over time. So you're not doing kind of like those big steps that are sequential if you were using that other method. And this just summarizes the boundary conditions that can be used for each kind of analysis. So you can see, for instance, that in the semi-coupled and fully coupled, the seepage boundary conditions can be applied, whereas for semi-coupled, you cannot use some of these other drainage conditions or non-consolidation conditions that you can use in this method. But fully coupled can basically cover everything. So it would be like the most complete, but also takes a little bit more time to set up based on the more advanced boundary conditions. So we're going to jump right into the training itself, the tutorial. We'll be comparing these two methods. We will be starting a project. We'll be working in 2D, and just keep an eye out that our time unit will be days. And so from here on out, I'm just going to open the program directly and show you the steps. But basically, we'll be importing the geometry. It'll be a DXF file. And we'll also be importing the materials from a final file, which we'll also be including in our webpage when you download if you want to look over the video. This is where we put the recording, and you can download the PDF as well as the training material. We'll include the final file, so you'll be able to directly import these materials. But you've seen in the table, so if you wanted to, you could also just manually type that. So let me just open the program so we can get right into this, but I'm just going to basically start from this step, which is the meshing. So this is GTS&X. I've already told the program that I want to work in 2D. You can see that because our coordinate system here is pointing to the y-axis being in the vertical. So we're on the XY plane, hence it's 2D. And you can see our units down here, we're working in days as the time unit. So I'm going to go ahead and go to Mesh to import the materials and the properties from a final file. And I can also, actually, let me just go ahead and first import the geometry. I'll go to the main menu, import, DXF2D, and I'll select this CAD file that will also be included as the initial materials for the tutorial. I'm going to deactivate this grid since I already have the final geometry. And now I'll go to Mesh, and I'll go to Property to import the materials from a file that's already finished. And I'll just import all four. So as I mentioned, the main one will be the one we call here AC, which is the canned clay for consolidation. So we'll go right into meshing. We'll generate 2D meshes, and we'll use the auto area method. So I'll just draw a rectangle first over the embankment, and I'll give it a size of elements every basically 1 meter by 1 meter. And just give it the mesh set a name. I can preview the distribution of the size of the elements with this command here. And so that looks like a good size for me, but it's also a good practice. And if you're not quite sure what size of elements you're using, you can always preview it beforehand. But we'll just leave everything here at 1. So basically it's a 1 by 1 element. This will be the first layer. So we could just call it AS1. Remember, it's the first layer of sand. And then this will be our clay layer, and we can select all of them. And we select the material here, AC. This will just be our clay. And then lastly, our last layer, which is our second sand layer. We can just say AS2. So we've completed the meshing, and now we can go right into what would be the boundary conditions. And this is where it's going to get, we're going to apply several boundary conditions. Some of them will seem like we're doing the same thing over like more than once, but this is just to show for the different methods that we're using, which boundary conditions are used for what. So the first would be to define the water level, initial water level for the, I guess, most methods, but this is mainly how you would do it for the consolidation analysis. So you would select the water level command, and you can just select the geometry, basically edges, where you want the level exactly to be. But again, this is assuming a steady state scenario, or at least initial, the first stage will have that condition. So we apply the water level, the initial water level, and then we're going to do some of the other boundary conditions, like, for instance, the suction drains. We can apply those using the nodal head boundary condition. So here you can select by various methods. We'll select the edge, and we can just select the vertical lines of where the drains would be. And we can directly input here a pressure, even negative. So we're going to give it a -5. And this being just for this distribution, it's a practical suction pressure. This is what we're creating basically. So we give it a -5, and then we also have to give basically a name that we can find in our stages. So this will be the boundary condition for suction. And you see these icons distributed in the geometry. You can also apply this directly to nodes, and you basically try to select capture all the nodes along the line. It's in the end, it's the same result. It's just easier to apply using the edges as the selection method. So now we're going to apply the other drainage conditions for the case of the embankment. But in this case, we're directly going to create the pressure distribution. So we're going to set one pressure at the top of the clay layer and then a second pressure at the bottom of the clay layer. So this would be draining or drainage by total head. And the distance between the top and the bottom is 10 meters. So I'm applying a pressure head of 2 meters at this layer and then one of 12 at the bottom layer. But I'm keeping in the same set, so they'll be activated together. Now we're going to apply the drainage condition for the specific drainage condition that we have seen that's useful for consolidation analysis. And we're actually going to apply it to the same places as we just did for the total head. We select both the top and the bottom layer of our clay layer. So this will be drainage for consolidation method. And lastly, we will apply this non-consolidation boundary condition to the embankment. So I can select directly, instead of trying to select the nodes, I can just set the set directly from the workstream. So we don't necessarily have to use this boundary condition, especially since we're comparing like a one-on-one to the fully coupled method, but this training is mostly just to show you the different commands that you can use and how to apply them. But it's not necessarily saying that if you're doing a consolidation analysis, you have to use the non-consolidation boundary condition. It's just there in case you're looking to apply something like that. So then we will apply the stress constraints, or the constraints for the stress analysis part. So in this case, we will just go to auto, and this will just be the ground boundary condition. And the program restricts the degrees of freedom automatically, so laterally and vertically for the bottom, as you can see on the icons. And then the only loads we're going to be using today will actually just be the self-weight, but you can apply pressure loads or displacements or forces as well over any part of your model if you like. So here we're just telling, making sure that gravity is in the -1 direction. This would just be for self-weight. And we see the icon there. So now we will proceed to create the stages, construction stages. We're going to create 3 cases, as you recall. 2 of them will be fully coupled, and one of them will be consolidation. So here from the list for construction stage analysis, we see several options. Stress, seepage, slope is actually the semi-coupled option, which we had done in a previous tutorial. And as I mentioned, this goes almost like sequentially. It goes from back and forth between seepage and stress in each stage. We're going to be working mostly with 2 of them with fully coupled and 1 in consolidation, where the stress and the seepage are both considered in the same stage. So let's first just create the case for the suction condition. So I'll give the name for the construction stage is suction. It's a fully coupled, and I'll click add, and then I'll just select it and go to define stages. What we get is this kind of table. As you see now, for the semi-coupled, if you clicked here on the drop-down, you will see between the 2, stress and seepage here, there is no option, it's already together. But the other main difference is that you have to define a time step, a duration to each stage. So this will be the initial. And what we're going to do is we're going to drag and drop from the set data window into the activated data window, so that we can tell the program what's going to be considered in this stage. One way to keep track, an easy way to keep track of what's happening is to change here the option in show data to only what's been activated so far. So we see nothing has been activated. We can kind of see it if we drag our window a little bit out of the way, or if we zoom out with the scroll on the mouse. So what I'm going to do is I'm going to start dragging my sets, and you start to see them appear. Oh, sorry, this is on deactivated. Activate. You start to see them appear in the model. So it's one way to keep track. So for this construction stage analysis, we're going to activate everything except the embankment. So here I'm missing one of the clays, so I'll just try capturing them all. Okay, there we go. So see how it's easy to make sure you have everything activated by just changing this to show data. We want to activate our boundary condition for the ground, and our initial also wants to have the self-weight. We're also going to activate the water level. So I'll go here to define water level, and I can just give it directly a height based on the global origin, but we had actually selected from the geometry directly where we want the water level to be. So I can select it here from the drop-down menu, and then this becomes a multiplier. So I want to keep it as a 1 for this stage. The last thing we need to define is the time step. So we click here, and we're going to say just this step is 1 day. We activate save result, and we generate the step. And since it's customary, just clear the displacement on your initial stress stage. So whatever you see results moving forward is strictly due to whatever you're activating or whatever boundary or load you're applying. So we click save, and then we go to new. This will be the suction stage. We're going to activate our boundary condition of the drains. So we activate this boundary condition here, suction, which we can see through these icons. And this will last for 100 days. This stage lasts for 100 days. The step number is basically, you can break down into number of steps, if you will, how you want the results to be seen. So we can, if we want to see the progress, we can just give this, for instance, every 10 days I'd like to see a result. So I'm going to break down 100 days into 10 stages or 10 steps. But, again, actually, if you want, only give it a value of 1 and you would see the final result of 100 days. But this allows us to create better graphs when we're extracting results, especially something like this that's changing over time. So we're giving 100 days and we're breaking it down into 10 steps. And we save. And then we create the next stage. It would be like the leave time. And what we're going to do is we're going to deactivate the suction boundary condition. So we had activated this boundary condition previously, and now we drag and drop it into the deactivate data. So it will no longer be considered for this stage, and this stage will last, we'll say 1,000 days. But I'll keep the number of steps as 10. So we'll get results for every 100 days. And we go to save. So this is a very simple analysis, and so hence it only takes three steps. Basically, we're using a boundary condition, a drainage suction boundary condition, to create a settlement, a compaction of the soil. And we want to compare that versus not having that drainage boundary condition of suction, but just having the weight of the embankment itself. So we could actually just go ahead and create a whole new, define two other cases, each with the same 3 stages, one by one manually. But the program also allows you to create copies of what you've already defined, and then you can just go back and modify whatever it is you need to do. So for instance, this will be the fully coupled embankment case. So I'm changing the name first here to modify, just so that it's easier to keep track. And then once I've done that, I can click it and go to define. And we see that it's saved the information from the previous case. So in this case, stage 1 initial is the same. Here now, we're not using the suction drainage condition anymore. We're just going to activate the embankment. So I'll change the name, and I'm going to deactivate this boundary condition, but activate the set embankment. And we click save. The time step, since it's the same kind of analysis, fully coupled and fully coupled, that information was saved. But we'll see later, for when we change the last one to consolidation, we have to reapply that information. So the leave time, the last stage, is actually the same as well. We just leave the embankment activated, and we give it the same time duration, which, as I mentioned, is saved. So we can close this stage. And the last one will be for consolidation method with the embankment. And what I'm going to do also is select from the list the other type, consolidation, and go to modify. So here it's letting me know that because we changed the type of analysis, some of the information was lost. So when I am defining it, I have to pay attention for some of these things. So for instance, the water level was not saved. Information about the time step was also not saved. So just making sure that all this is been defined in your model. So here stage 1 is actually going to be exactly the same. We want to activate the water level the same. Stage 2, however, this again will be embankment. And so I'm going to deactivate this boundary condition, activate the set. But we're also going to activate the drainage condition and non-consolidation method. The time duration is also the same. So 100 days over 10. And then the last stage, the leave time, will be the same. There's nothing else happening except that we need to define that it's 1,000 days or 10 days or 10 steps. So I just realized that I forgot to activate the boundary condition for stage number 2 here, or case number 2. So here in the second stage, we activated the embankment. We also want to activate our head draining condition for this stage. So that was one thing I just realized I missed. So for the fully coupled embankment, we have our own drainage condition, but we're using the head, difference in head, as the drainage. So we have the three cases created, and now we just need to define the analysis case for each so we can run the analysis. So we go to analysis, general, and we're going to create one for each case itself. So we select from the solution type, construction stage, and basically we can give it the same name. Here are the three stages or sets we have created. So the first case can just be suction, and then analysis control. We want to activate the stress, initialize the stress at the first stage. We want to activate the estimate initial stress of the activated elements, automatically consider water pressure, and estimate initial configuration for nodes. There's also nonlinear behavior that we want to capture. So we'll go to the nonlinear tab, and this is actually only very useful for these kind of fully coupled analysis. So we want the pore pressure to be updated with deformation related to the stress. So this is when these conditions, geometry nonlinearity conditions, can be used. So that would be the case for suction. We can go to apply and then just repeat for the other ones. So fully coupled embankment, and we just repeat everything the same. And then the last one would be for the consolidation. And then we can just perform the analysis for all three. So for time's sake, we will open a model that's already finished. So this is at the stage where we're at, and you can see when you download the PDF, it'll kind of highlight for you all the, in case it wasn't easy to follow with the cursor of the mouse. You can follow whatever we were activating directly from the tutorial, and there's a brief explanation on some of these conditions that we specified in the analysis control, just to clarify what these initial configurations differences are. So these are specific for these kind of analysis where you're activating, constructing embankments, if you will, and deformation can change the pore pressure and such. So here's a quick summary of the comparison between the results for the different methods. So here we're looking at pore pressure. Let me make this full screen. I'll just quickly scroll through this. Here we go. So here we're looking at the difference in the results for what would be first the pore pressure. As we see between the two embankment methods, we have a pretty similar distribution with the exception that because we applied a non-consolidation boundary condition, there's not going to be a pore pressure information for the embankment. However, had we not applied that boundary condition, we would have seen something similar to this, a negative pore pressure. The water level is right at the top of this boundary, since that's what we initially defined. And this is what you would see for the suction, the fully coupled method, but when we did the suction condition. So we see similar distributions for the cases that are the most similar, which would be the ones with embankment. And in terms of settlement, here are the results for all three. So again, we see very similar results for the embankment method. Essentially, we try to recreate similar boundary conditions, and so this is what we would expect anyways. But we see a settlement of around 0.6 meters. For both cases, and the distribution itself is also similar. And for the fully coupled suction method, we also see in the same range, similar what would be settlement. In this case, it's being created by the suction itself, the drains. But you can see how this can be considered a method of improving the soil beforehand, or some sort of special case that maybe the embankment, for this needed to happen before the embankment is constructed. The soil needed to be improved for some specific condition. You couldn't just go ahead and start the construction of your embankment. But in itself, we were also trying to recreate a similar distribution as what we saw for the embankment case. So I'll open the model now and show you some of these other tools and features that we have to extract these kind of results. So in this case, we're going to use the extraction tool to look at settlements, displacements in the vertical direction for all three cases, and how to graph that in Excel so you can have the data compared one-to-one. But basically, this is what we're going to see, that the fully coupled and the consolidation cases for the embankment are basically giving you the same kind of settlement result, whereas in the suction, the initial stages that had that suction condition activated, we're seeing a much larger displacement initially, and then once that suction condition is turned off, we see that the soil is recuperating or expanding back slowly. So that's kind of like the behavior that we're capturing in these graphs, and why it's useful to add those steps in the time steps when you're defining the stages, so you can get data at multiple points and you can see what's happening over time. So to get these kind of results in the program, let me open the model that's already finished. So we would go here to we're in the post processor now. This is our results tab. First, just to give you like a introduction to how you see these results. So you see here that the results are going to be grouped. Each will have its own three stages. You can kind of expand or summarize each of them here with the plus or minus sign. So we have the three sets of analysis, and each has its own stage. So you can go to the last stage of the last lead. You see here how we broke it down into 10 steps for this stage. So you can go to the last stage, settlement results, and this is how you would see it. So you can go to also total translation or just the vertical displacement. Here in the properties tab, there's a drop-down menu. You can go to legend, and if you scroll down, you can turn off the exponential option for how the results are portrayed. You can change the number of decimal points if you like as well. You can use this max min option to show you directly where the maximum and the minimum values are located. You can create an animation, multi-step animation here on this menu. There's a camera that allows you to activate the multi-step animation, and then there's another icon here that allows you to select which stages if you want to consider for the animation. And once, in this case, we're going to select all of them, we can go play, and we will see the change in results. We see the bar down here basically going through the stage by stage, which is time. And that max option being turned on, it updates automatically for each stage. So we can see the procedure of this construction method over time. And we can actually save this as an animation, as a video that you can put into a PowerPoint presentation or whatever kind of presentation you like. So this multi-step animation recording is pretty handy for these kind of analysis when there's a lot of change or a lot of movement over time, settlement over time. So that's with the max min option on. We have different commands like probe, where you can manually select nodes of interest if you wanted to make like a straight line more or less to give you an idea of what's happening. And this also stays activated even if you're changing type of analysis or type of result. Those will stay on. But the one that I'm showing you for the graph will be this one called extract. So you see here when we use this extract results command, you will have the case analysis here, the sets. So we're going to repeat this for each one. Here's the type of result you want to see. In this case, we're going to do displacements, and we're going to do total displacements. And then we're going to select all the stages. And here's where you select which node. You can select multiple nodes. Let's just try to do the one right at the center of the embankment, right there. And we'll just generate the table. And so we see the results here. I am going to select two columns and right-click to send to Excel. So I'm just going to give it a name like settlement. Save. And so we get this file created, this Excel sheet. And what I'm going to do is I'm going to repeat this process. I'm just going to select from here the other two cases and select the same result. The node actually is still selected, so we want to use the same node. And here now I've created a new table. I can actually just select this, and with my keyboard, just copy it, go Control-C, and go back to my Excel and paste it. Sorry, I want it to be on the same. And then I'll just repeat the same for the last stage, which is the suction. Control-C, and then just paste it. And then here in Excel is where you could select this would be like the steps, or you can do it if you like by time, but as long as you keep it consistent, you can graph it however you like. Wrong button, sorry. So we select all of them, and then you can just create your graph. Nope, wrong chart. I think I selected the data incorrectly, sorry. I made a formula for some reason. Oh, basically, you graph this directly into Excel, and then you can bring it back if you like. So here we go. So in this case, I did total displacements, but you can also do just directly settlements, and the graph will actually look inverse for the negative values. But you can see, you can then assign the names and see the similar results. The other thing you can directly also do is, if you wanted, for instance, consolidation, as I had mentioned, analysis gives you result for excess pore pressure. So you can go to plane strain stresses, excessive pore pressure. So this is one result that we can see in the consolidation method that we could not see in the fully coupled. We would have to manually, in the fully coupled graph, what would be the pore the effective pressure and the total pressure, and manually calculate the excess pore pressure, because this won't be, it's not activated as an option of the results. You can do it, but like I said, you would manually graph this, whereas with the with the consolidation analysis, so we have here the consolidation, I can directly just extract and graph my change of pore pressure over time. So we'll go here to plane strain stresses, excessive pore stress, and I could select the node somewhere in the middle of the drainage, and then just directly within the program also just graph that change over my steps. So these are different kind of tools. So you can graph it internally or just export it to Excel. But those are some of the key tools that you can use for these kind of long-term changes, results. So this is what we were looking at, some of these different behaviors, kind of settlements related to the suction period being activated versus when it's removed, as well as the pore pressure for the consolidation analysis. And then lastly, we will include this file in the final files folder for whoever wants to give it a look. But we just wanted to give you a quick comparison of, this is a case we've done in the past, and as I mentioned, we did it as a semi-coupled analysis where we change between stages, between seepage and stress stages. So in these kind of semi-coupled or sequential analysis, what you would see in the post-processor would be the types of results grouped. So for the stage of seepage, you would only see seepage results. And then for the next stage, where we see here as stage 2, we see all the stress results like displacement, stresses, strains. Whereas, as I mentioned in the fully coupled, you see both kind of results in each stage, displacement and nodal seepage together. And so you'll also notice that for the fully coupled results, you don't have these bigger steps, these bigger changes as drastic as you're seeing kind of for the semi-coupled, because you can do this, you can control the time. It's not just controlling a stage step, but you can control the time step for each stage. And so you get more data. But in the end, for this very simple condition, the simple model, you can get similar, we got similar results. But we just wanted to point out some of the differences in the procedure and how you see the results between the two methods. And so you would have to take into consideration now what exactly you're modeling and how accurate you want it to be. You can always have preliminary results as semi-coupled and then run one final stage when you're all done as the fully coupled. And this would be for that same model for the changes in the pore stress, pore pressure head under the two conditions. But that's basically the end of this training.